Good day everyone and welcome to MPI 2022. With a pleasure, today we would like to introduce our research product, namely an advanced neuro-computing based on physical representation for solving various types of PDE. I am Dana Adi Pratama, the leader of this project, with Dr. Maharani Abu Bakar and Dr. Nurbaini binti Ismail. We are from Faculty of Ocean Engineering, Technology and Informatics, University Malaysia, Terengganu. To begin the presentation of our research, there is a question. Why do we learn partial differential equation? Well, the simple answer is because the partial differential equation or PDE describe how nature works. Many of the phenomena in natural, scientific field, engineering, and technical problems can be modeled and analyzed using PDE. That's why how to solve PDE fast and accurately is continuity research. Numerical methods have been investigated to solve PDE, such as Runge-Kutta, finite difference, finite element, and etc. However, these methods are required a lot of memory space and time. Consequently, the approximation process becomes expensive. Recently, researchers emerged artificial neural network or ANN based method for solving PDE, and it has been investigated since decades. With the nature of ANN architecture, it enables us to hybrid with any optimization technique such as gradient descent and etc. In this project, we hybrid ANN-based method called Self-Adaptive Physics-Informed Neural Network or SA-PINN with the genetics algorithm and L-BFGS optimizer to form a new neural self-computing called SA-PINN-GA-LBFGS. Let's have a look at how our method works for solving the PDE. Firstly, we have to define our PDE problem. In this case, we solve the second order PDE in the form of this, and then the initial and product condition of the PDE above is this equation. Next, we define the ANN architecture. As an illustration, let us assume a 3-layer perceptron with input X and T, a single hidden layer with 2 neurons, and a single output U hat as an approximation function. To approximate the unknown PDE function which is U hat, the weight and the bias are stored inside a variable called theta, and this variable must be updated to make the loss function as minimal as possible. To update the theta, we employ the genetics algorithm evolutionary process to run M generation iteratively. Alright, in a GA process, we initiate the population matrix which consists of several theta and it looks like this. We then apply each theta in the population matrix of the ANN architecture. Suppose we apply the theta 1 to our architecture. The visualization of the process is look like this. So, we will obtain the loss function. Similar process have to done for all theta. The next process is selection. After we apply all theta inside the population matrix, we will obtain loss function value correspond to each theta. The loss function value has to be sorted from the best to the worst value. Then, the two thetas which is produce the smallest loss function will be selected as a parent. Next is crossover and mutation process. Crossover actually is a process that makes weight and the bias between the two parents to produce the new child. The process is visualized like this. After crossover, mutation takes place. Mutation is an important process to prevent the local minimum problem in GA. The process is quite simple. We only change the weight or bias value within the child randomly. How many values change is based on mutation rate. All of the GA process from the initial population, selection, until mutation will be done over and over until the last generation is reached. It will be produced the theta B, which is the best theta. After the final of genetics algorithm or GA, the theta B will be continually updated using L-BFGS algorithm. And here is our Neuro-Computing SA-PINN-GA-LBFGS algorithm. We test the performance of our proposed method using three types of hyperbolic PDE, parabolic PDE, and also three types of elliptic PDE. Here I want to show to you for the elliptic one. The exact solution is defined by this equation and visualized by this figure. Then, these are the approximation results using our method. You can see that overall, the approximation result is quite similar to the exact solution. In the last history comparison, our method, which is in the red line, also gives better loss function value compared with the existing methods that use Adam and Adam L-BFGS optimizer. The last result is the simulation of ANN architecture. In the simulation, for elliptic PDE as an example, we using three different types of layers, which are 3, 5, and 8. Each layer will have 10, 20, and 50 neurons, while the other parameters such as the training point and iteration are remain the same. Here I want to show to you the simulation result for all test problems. Based on the result that I mentioned earlier, there are several points to discuss, and this is the three main points that you have to consider when using our method. Okay, I think that's all for my presentation. Thank you very much for your attention. Thanks for watching, and Assalamualaikum warahmatullahi wabarakatuh.